Okay, guys, so for today's lesson, we started talking about a new type of distribution called the Chi-Squared distribution. And it's used anytime you're doing a significance test on more than one population or more than one group or a group that has several different categories. You can even use it to compare multiple variables. We're going to start by reviewing the example we did in class today with the activities with M&Ms to see if the distribution of colors in M&Ms matches what the company's claim is. So we did an example of the Chi-Squared test for goodness of fit today in class, and I'm basically just going to review with you how to set up the hypothesis test and how to calculate the probability or the p-value to know whether or not your null hypothesis should be accepted or rejected. So again, suppose you open a 1.69 ounce bag of plain M&M chocolate candies and discover that out of approximately 56 M&Ms, there's only a single blue M&M. Knowing that 10% of all plain chocolate M&Ms made by the company are blue, and your sample size of 56, obviously you think you probably should have more than that. The proportion of blue M&Ms in your sample is only 0.018. That's 1 out of 56. And so you might feel that you didn't get your fair share because there's supposed to be 10% of blue M&Ms in that bag. So you could use a z-test here, because if you're thinking about your proportion of blue M&Ms, you should think that, the null hypothesis would match the company's claim of 10%. And since you suspect you've been gypped, your alternative then would be that the proportion of blue M&Ms is actually less than that. And you could do a one sample or a one proportion z-test and calculate the probability of getting a value as extreme as the one you got. So you'd essentially be finding the probability that p hat is less than 0.018. Given what you know about the distribution. So again, p is the proportion of blue M&Ms. You could then perform additional tests of significance for each of the remaining colors, but this would be inefficient because if there's 5 or 6 colors in the bag of M&Ms, you're doing 5 or 6 different tests. More importantly, it wouldn't tell us how likely it is that the 6 sample proportion differ from the stated values as much as our sample does. But there is a test that we can do all of this at one time, and this is called the Chi-Squared test for goodness of fit. And I think some people were saying that they actually have done this test in biology. So we're going to look at another example. This example, we have in recent years the expression the graying of America has been used to refer to the belief that with better medicine and healthier lifestyles, people are living longer, and consequently, a larger percentage of the population is of retirement age. And we want to investigate whether or not this perception is actually true. So you're given the distribution of U.S. population from 1980, and so notice that the age groups are broken into categories. The categories don't necessarily have to be the same number of years in each category. It looks like this is pretty close though. So we've got 4 different categories or 4 different age groups, and then you see the population in the US in 1980 split down by counts. And then you can also see in the third column that you're given the percentage of the population, and this is actually the value that is going to be most helpful to us, is knowing the percentage breakdown of each of these categories of age groups. And so basically we want to determine if the distribution of age groups in the United States in 1996, sorry my data is still pretty old, was significantly different from the distribution of age groups in 1980, so 16 years later. So we're going to perform the following hypothesis test. So notice with the Chi-Squared test of goodness of fit, we're writing out our null and our alternative hypothesis. So we're basically saying as our null hypothesis that the age group distribution in 1996 is the same as the 1980 distribution. And our alternative, and this should actually be the letter A, sorry. The alternative hypothesis then would just be that the group distribution in 1996 is different from the 1980 distribution. So we're not doing a one-tailed or a lower or an upper-tailed. We're not looking at the distribution being less than or more than. We're only looking at whether or not the difference is, we're only looking at whether or not there is a difference in the distributions. So, but it's not actually considered a two-tailed test, and I'll show you that in a little bit. But our null and our alternative hypothesis can only be written out in words. The idea of this test then is basically that we're going to compare the observed counts for our sample from 1996 with the population or the population with the counts that we would expect in the 1996 distribution if they were the same as the 1980 distribution. That is, if the null hypothesis were in fact true. So the 1980 distribution is going to act as our population, because that's pretty much our frame of reference, and we're looking to see if our sample differs from that. So the 1980 distribution is going to act as our population. And the more the observed counts differ from what we would expect, the more evidence we have to reject the null hypothesis, and then conclude then that the population distribution in 1996 is in fact significantly different from what it was in 1980. Okay, so here is a random sample of 500 US residents in 1996. So this is our sample. Okay, this is what we actually observed. So our sample is what we always observe. And so this gives you, again, we have a sample of 500 individuals, and we're given the counts. And we're also given the percentages, which is fine too, for this particular group. But we're really most interested in the count. That is actually what we're going to be using in our test. And just like with any other test, if you have data, it's good to always graph it just to kind of get a sense of what's going on. And so if you look at the 1980 distribution of age groups versus the 1996, you can see in 1980 there was definitely a larger proportion of younger Americans than there are in 1996. And so you can also see that in 1996, it does look like the proportion of individuals that are over the age of 65 is slightly larger. And so I don't know how clearly that difference is, but it does look like there's a difference here. So this, my board isn't calibrated, but that's not working at all. Anyway, it does look like there is a slight difference in the proportion of individuals that are over the age of 65. So what the Chi-Squared test will do is to determine if that difference is actually significant, if it's something that is likely due to chance, or if it's something that is due to the change in the distribution. So our next step then, if we know the population percentages from 1980, what we want to do now is if we're taking a random sample of 500 individuals, so if n is 500, I want to figure out, based on the 1980%, how many individuals should I expect to be from 0 to 24 in my sample? How many individuals should I expect to be between the ages of 25 and 44 in my sample of 500? So the way we calculate our expected counts is simply to take our percentages, and we're going to need to move the decimal points over, and multiply them by my sample size. And that's going to give me the expected counts. Okay, and so if we use our graphing calculator, I would expect, in a sample of 500, I would expect 206.95 to be between the ages of 0 and 24. And if you multiply the next group, we should expect 138.4 to be between the ages of 25 and 44, and 98.2 to be between 45 and 64, and 56.4, and round to 3 decimal places. You should also double check to make sure that these values do in fact add up to 500. If you're slightly off, like I am, it's just due to a rounding error. Okay, so the next step then would be to determine basically your chi-squared value, which is basically determined by taking the sum. I probably put the parentheses in the wrong place, but anyway, of your observed minus the expected values from your sample squared, and then divided by your expected values, and then adding up all of the values from your from each of those categories. And the sum is basically going to be chi-squared, and it just looks like an x squared. And that is called the chi-squared test statistic, and that's what we're actually going to be finding the probability of. So I've just organized this into another table, but you can actually do all these calculations in your calculator. So for example, and I'm not going to write them down. I'm just going to type everything into my calculator instead of writing everything into the table. And you can do the same. On your test, obviously, I'm going to want to see that you've done this, but we're basically going to do all the work in our lists. So in list 1, this is where I'm going to put all of my observed values. And remember, the observed values, let me just clear out those lists. The observed values are basically what I saw in my sample. This is the count from the sample. The expected values would be the expected counts. So basically, those are the values we just computed, where you're taking the percentage from the original population or from the 1980 population and multiplying by your sample size. Okay, so we were given the values of our observed numbers. So there were 177 between the ages of 0 and 24, 158, 101, and 64. And those are the values that were given to us. Let's see. Yeah, so this was our, these were our sample values. So those are the observed values that I'm putting in the very first column in my table, in my calculator. Okay. And then in the second column, I'm going to enter in those expected values that I just calculated, the 206.95, the 138.4, the 98.2, and the 56.4. And so that's my expected. And so in column 3, this is where I'm going to do my observed minus the expected. Well, my observed values, I'm going to put this in parentheses. My observed values are coming from list 1. I'm going to subtract my expected values, which are in list 2. I'm going to square that difference, and then I'm going to divide by my expected values, which are again in list 2. And that's going to give me a bunch of numbers. The chi-squared test statistic is the value that I get when I add those 4 numbers together. So all of those numbers are in list 3. If I go back to my home screen and hit second stat, I can now do my math operations on my list. And so basically what I want to do is take the sum of list 3, and I get 8.214. That is my chi-squared test statistic. Okay, and so that answers part C. Determine the sum of the values in the third column. This is chi-squared. The larger the differences between the observed and the expected values, the larger our chi-squared value will be. And therefore, that's going to give us more evidence against the null hypothesis. Now, we haven't, we're going to talk about degrees of freedom in just a second, actually. Let's go ahead and jump to the next page. So let's talk about the chi-squared distribution. It's basically a family of curves that are used to assess the evidence against the null hypothesis, represented by the value of chi-squared. The member of the family that's used is called the degrees of freedom. So we've seen degrees of freedom before. This is the only parameter for my function. And since we're working with percentages, basically 3 of the 4 percentages are free to vary, but the 4th one is not, since all 4 have to add up to 100. So in this case, we have 3 degrees of freedom. And it's, instead of taking our sample size minus 1, we're looking at the number of categories minus 1. So degrees of freedom are equal to the number of categories minus 1. And this is for the chi-squared distribution. So it's not the sample minus 1 anymore, it's the number of categories. And just like with the normal curve and with the t-distribution, you do have a table of values that will give you all of the probabilities for the chi-squared distribution. I'll also show you how to do this on your calculator because it's a lot easier. But I'll show you the table in just a second, but it basically shows you the typical chi-square curve with a right-tailed area shaded. The chi-square test statistic then is just a point on the horizontal axis, and the area to the right is the p-value of the test. So actually I'm going to scoot over to the next slide for just a second. So this is what a chi-square distribution looks like. It kind of goes up and there's a hump, and then it's skewed to the right, and it's always going to be skewed to the right. Your chi-squared value then, anytime you're doing the hypothesis, it's always an upper tail. It's always going to be an upper tail probability. And so your p-value is always going to correspond to the area on that upper tail. Okay. Let's see. The larger the value of the chi-squared statistic, the further it's going to be along the axis. So the larger this value, this is just an axis that starts at 0 and continues. So chi-squared will never be negative. So the farther along your chi-squared value is along that axis, obviously the lower your probability, the lower your p-value. Let's see, and the more evidence, obviously. If your p is small, then you can reject the null hypothesis. So some other properties of the chi-square distribution. Again, like I said, it's a family of distributions that can only take on positive values, and it's always going to be skewed to the right. A specific chi-square distribution is specified by only one parameter, and that's the degrees of freedom. So you're given several different curves that kind of show you the shape of the distribution as the degrees of freedom increase. And I think you can kind of see that as they increase, as your degrees of freedom increase, obviously your sample is getting larger, and so your curve is going to approach that of a normal distribution. And so it says, what happens to the density curve and to the p-value as the degrees of freedom increase? So as your degrees of freedom increase, if you think about, let me see, let's say, that's my cutoff. As your degrees of freedom increase, the area under the curve is also increasing. So there's more value when you have the cutoff. Okay. All right, so a couple other properties. Obviously, just like with any density curve, the area underneath the curve has to equal 1. Each chi-squared curve, like I said, begins at 0 on the horizontal axis, increases to a peak, and then approaches the horizontal axis asymptotically, which basically just means it never touches or crosses the axis. None of the density curves do. Each chi-squared curve is going to be skewed to the right. As the number of degrees of freedom increases, then the curve becomes more and more symmetrical and looks more and more like a normal curve. This is an example of your chi-squared table. And it's similar to the t distribution in the sense that not all of your degrees of freedom are shown, and you're not always going to be able to find an exact value. So in the previous example, we found that chi-squared was equal to 8.241. So we essentially want to find the probability that chi-squared is greater than 214. We also know that there were 4 different age group categories. So the degrees of freedom for this distribution is going to be 3. So if I'm going to use the table to find the probability, I'm going to first look for my degrees of freedom, and then along the line I'm going to look for my chi-squared value of 8.24. So if I look down this line for 8.24, I can see that it's between 7.81 and 9.35. So if I go to the top of the table, that gives me a range of p-values. So all I can really say is that my p-value is between let's see, 0.025 and 0.05. And so my p-value would be significant at the 5% level since it is somewhere less than 5%. So that means I can reject my null hypothesis, and I can conclude then that the distribution of age groups has changed since 1980. If we want to do this on the calculator, we can do that as well. So if I pull my calculator up, I'm going to go straight into my second distributions, and you'll notice options number 6 and 7 are our chi-squared distributions. Just like with the normal curve and with the t-distribution, anytime you're dealing with a density curve, you never, ever, ever want to choose PDF because it's a continuous curve and you'll never be able to find the probability that x equals a single number. So we never want to use the PDF. That's only used when we're actually graphing the function. We're going to choose the Chi-Squared Cdf. And you can see in the notes, when you're doing the Cdf, you enter your lower bound, your upper bound, and then the degrees of freedom. If you have one of the newer calculators, it'll prompt you for this, so it makes it a little bit easier. I don't want to lose any of my decimal places, so I'm going to use my second answer key. That's my lower bound. My upper bound is 9999999, and the degrees of freedom we know are 3. So when we calculate the p-value, we get something more exact, and it's 0.0418. Okay, and so again, we can see that that value is significant at the 5% level. We can reject our null hypothesis and conclude that the distribution of age groups has changed. So just to summarize, for a chi-square test of goodness of fit, I actually think the goodness of fit test is pretty easy. The one thing that you can't do, though, in fact, let me show you. On your calculator, if you go into your tests menu, you will see, if you scoot down, you will see a chi-squared test. In fact, let me just see if there's any other. The chi-squared test that is on here, though, is only used when we're dealing with two different variables where we're actually comparing, like if I wanted to, I'm trying to think, in the M&M example, for example, when we were looking at the different M&Ms, if I wanted to look at the distribution of colors for the plain M&Ms versus the peanut M&Ms and the peanut butter M&Ms and the pretzel M&Ms, I could do a different type of chi-square test, and that is the kind of chi-square test that this option on your calculator allows you to do. The test for goodness of fit is something that you have to sort of do by hand. You actually just have to use the Chi-Squared Cdf to calculate the probability. And next class, we'll talk about how to do the other kind of test. It involves using matrices in the calculator, which I'm not sure if that's something that you guys have done in previous math classes or not, so it may take a little bit of time to cover that. But the test of goodness of fit, again, we start off with the null hypothesis. That is basically the actual population percents are equal to the hypothesized percents. The alternative would just be that they're different. So you always have to write out in words what the null and the alternative hypothesis represent. Our chi-squared value is simply equal to the sum of the observed values minus the expected values squared and then divided by the expected values. These numbers are always represented as counts. So even though you're going to be given some percentages, you always want to take the percentage and multiply by your sample size to get a count. So you'll have an observed count, an expected count, and so we're always looking at the counts. Then chi-squared has an approximately chi-squared distribution with n-1 degrees of freedom, where n-1 is the number of categories. -1, that's your degrees of freedom. So just be careful with the n. N doesn't necessarily represent the sample size in this case. To determine your p-value, you're always doing an upper tail. It's always going to be greater than. You're always looking to see the probability that your chi-squared value is bigger than what you get from your sample. And it's easiest, obviously, if you just use the chi-squared command on your calculator. The conditions, though, are very different than some of the conditions that we've looked at before. You can only use this test when the critical values from the chi-squared distribution, when all individual expected counts are at least 1. So if you opened a bag of M&Ms and you didn't have any blue M&Ms, you wouldn't be able to do the chi-squared test because you need at least one blue M&M and one brown M&M and one yellow. So you need to have at least one count, and then of all of your categories, no more than 20% of them can have a count that's less than 5. So this is still getting to a place where we're saying we need to have a large enough sample to be able to do this test, but the conditions are different. So this is something that you definitely want to jot down and take note of to make sure that you have the right number of counts. But again, if you have a scenario where your counts don't match up with the conditions, then you just want to write a statement to use caution. You can still continue with the test. Okay, there are 2 examples in your classwork. I am going to get you started with one of them, and then I'm going to ask that you complete these 2 examples as part of your homework so that when you come into class, you're prepared to go over these, and then we can use class time to talk about the other type of chi-squared test and do some practice problems. So in this first example, it says genetic research indicates that the following proportions in the color of flowers should occur when cross-pollinating 2 species of the same flower shrub. So we're told that the ratio of red to pink to white flower should be 2 to 5 to 1. So when we're dealing with ratios, you do need to sort of convert them into a fraction or a percentage. So if you add up all these values, so 2 plus 5 plus 1, that gives us 8. So out of the 8, 2 of the 8 should be red. Out of the 8, 5 of them should be pink, and out of the 8, 1 should be white. So you don't necessarily have to write them as percentages. In fact, I would leave them as a fraction so you don't have to deal with the rounding issues. In the next example, you're given a random sample of 50. And so you're now given the breakdown for your red to pink to white value. So these are your counts. These are your observed counts. And so it's really easy when you just plug these numbers into your table. So you want to determine if these results are consistent with the research findings. So your null hypothesis, and we're going to do this at the 5% level. So the null hypothesis, remember, we're just using words to describe the distribution. So we could say something like the distribution in color of flowers follows the ratio, and then you can actually either state the ratio or follows the ratio from genetic research, if that's what you want to write. So the distribution of colors of flowers follows, or is the same as, I think is how we wrote it, is the same as the ratio provided by the genetic research. And then the alternative would be the distribution is different. And just for the sake of time, I'm not going to write that all the way out. On the AP test, make sure you write it all out. Okay, and so we have 3 categories of flowers. We have red flowers, we have pink flowers, and we have white flowers. Remember the observed counts, that's your sample. And we're told we had 7 red, we had 33 pink, and we had 10 white. And so the total of that is 50. The expected counts, well, I know 2/8 of my sample should be red. So I'm basically going to take 2/8 times 50, and that's going to give me my expected count. I'm going to do 5/8 times 50, and that's going to give me my expected count of pink. And I'm going to do 1/8 times 50, and that's going to give me the number that I would expect to be white. And so these numbers, let me do them in a different color. So this would be, I would expect 12.5 of the flowers in my sample to be red, 31.25 I would expect to be pink, and I would expect 6.25 to be white. And if you add up all those numbers, I do believe they add up to 50. And again, you can enter these values in list 1 and these values in list 2. I'm just going to go ahead and give away that chi-squared should end up being 4.768, because remember, you're following this formula and then adding it up, which is going to be the sum of lists 3. And that is chi-squared. Your number of degrees of freedom, well, we have 1, 2, 3 categories. So your degrees of freedom is going to be 3 minus 1, which is just 2. And notice that all of the counts in each of the categories is above 5, so we're good to go. We don't have anything that's less than 5. And so if I want to find the probability, I'm basically finding the probability that chi-squared is greater than 4.768 when my degrees of freedom are 2. And so we can do this on the calculator. Again, we're going to go to second distribution. I'm going to choose my chi-squared PDF. My lower bound is 4.768. My upper bound is infinity, or 99999, and my degrees of freedom are 2. And we get 0.092. Well, at the 5% level, this value is not significant. Our p-value is not less than 5. And so I can't reject my null hypothesis, which means that I can't conclude that the distribution of colors in the sample is different from the claim made by the genetic researchers. And so that's what you'd want to write out in words. Okay. The last problem deals with the distribution of prizes in a box of cereal. And I'd actually like you to go ahead and finish this problem for homework. I think that it's laid out just the same as the previous ones. I think that you can handle following along and doing this problem on your own. So this is what I'm going to expect to see in class tomorrow, that you completed example number 2. Or not tomorrow, but whenever I see you next. So this is what I'm going to count. This will be your 10-point homework assignment. I better see this completed. Anyway, have a good night. I hope this was helpful. See you later.